챕터 5였나요? 알켄에 대해서 이제 좀 개론적인 거를 다뤘다면 이제 새 챕터로 들어가서 이제 본격적으로 좀 리액션에 대한 거를 다룹니다. 기말 범위에서는 리액션이 이제 많이 나오게 될 거예요. 그래서 올레진 더블 본드를 가지고 있는 알켄의 어디션 타입 리액션으로부터 이제 substitution, elimination 반응들을 이제 순차적으로 배우게 될 텐데 이제부터 정신 좀 차리셔야 됩니다. 중간 범위 때보다 조금 더 확장이 많이 돼요. 그래서 여러분들 선배들 보통 학업 성취도를 제가 한 3년 동안 트래킹을 해보면 중간 때 대부분 잘해요. 중간고사 때 평균도 꽤 높은 편이고 기말 때 차이가 엄청 나면서 점수 차이가 뭐 엄청나게 벌어집니다. 못하는 친구는 확 떨어지게 되고요. 그러니까 따라오지 못한다는 얘기예요. 팔로우를 잘 못한다는 얘기인데 시간 관리를 해서 조금 유기화학 원 기말 범위 내가 유기화학을 처음 배우는 거다. 특히 고등학교 때 안 배웠다. 그런 친구들은 시간 분배를 조금 더 하셔야 됩니다. 중간고사 때보다 많이 내용이 많아져요. 그래서 그거를 감안을 하셔서 학기 남은 학기 시간 분배를 다른 것과 잘 지혜롭게 하시길 바랍니다. 이제 기말 범위부터는 조금 예습 복습 좀 하시면 확실히 도움이 될 거예요. 유기화학은 익숙하게 만드는 게 중요하기 때문에 전날 벼락치기 한다고 될 수도 있고 잘 안 돼요. 유기화학이 이게 좀 연습이 필요한 학문이라 언어를 배우는 거와 비슷하다고 이야기를 했죠. 그렇죠? 그래서 수업 시간에 다룬 컨셉을 이해를 하시고 제가 최대한 이해는 하게 해드릴 테니까 이해한 다음에 본인이 연습 문제를 가지고 풀면서 자기 걸로 만들어야 돼요. Alright, let's begin the second half of this course. So we'll continue to discuss the alkene, but we'll focus on the reactivities. Okay, so discuss the reaction of the alkene for this new chapter, chapter 6. Okay, and for the second half of this course, we'll focus on the reactivities of various functionalities, and we'll discuss addition type reaction, electrophilic addition, and also elimination and substitution type reaction. So we'll study for the second half SN and E type reactions in addition to the addition type reaction. Okay? So we'll first study the addition, the electrophilic addition type reaction, and the key the reactant is the alkene. Okay. Yeah. So the first half is done, right? And we have now the second half. And as I mentioned, we'll study the addition type reaction and substitution elimination type reaction, right? That's the main focus for the second half. But in between, we'll perhaps learn about the delocalization a little bit, and then we'll move on to the SN and E type reaction, okay? And there are SN1 and 2, E1 and 2 type reactions. So this is the main focus for the second half, okay? All right, so we are getting into the chapter 6, the reaction of the alkene. Okay, and this is perhaps what we briefly discussed in the preceding chapter, chapter 5, the introductory part of the alkene, and this is the two-step reaction, right, for the electrophilic addition. Okay, and you have an electrophile here, right? If you have HX type molecule, right? And you can assign a plus on the hydrogen side. So this is serving as a electrophile, okay? And you have the electron-rich alkene. So first step is the following, right? The electron movement from this pi electron to the electrophilic hydrogen, and following the push-pull, right? Presentation, you can rationalize, right? This intermediate is formed. Which is called the carbocation. Carbocation intermediate because you have the cation on the carbon element. Okay. And for the first step, right, after first step, you are generating the reaction is generating, right, halide anion, right? And then this halide will attack this positive side. This is now serving as an electrophilic center, right? And halide attack the carbocation to formulate, right, the CBr bond. Okay. So as a result, right, you are getting the added product, right? Pi bond is broken, and there is new bond formed. New sigma bonds are formed, right, between carbon and hydrogen here, and carbon and bromo group there. Okay. And this is a two-step reaction, as we just studied. And first step is known as a rate limiting step or rate determining step, RDS. And the second step is relatively fast. Okay. So that is sort of like the mechanistic picture for the electrophilic addition. It's not that complicated, right? And there are some features that all electrophilic addition reactions have in common, right? This is sort of like a generalized formula. You have the olefin or alkene, right? And the pi bond there will be broken after addition type reaction. And you have, of course, the electrophile and nucleophile, right? And in the previous slide, we deal with HX type molecule, right? And this hydrogen side is serving as an electrophilic center for the first step. And the halide, right? After first step, the halide anion liberated from HX will attack, right, the carbocation for the intermediate to the intermediate, right, and formulate the final product. Right? So this is sort of like the three common constituents for the electrophilic addition type reaction. So one pi bond will be broken, right, from the olefin, and two sigma bonds will be formed. Right? And then the degree of hybridization will change, right? Initially, carbon on alkene was sp2 hybridized, and product side, right? Carbon after addition type reaction, right? Become sp3 hybridized. So this is the general features for electrophilic addition. And this is sort of like the exemplary reaction, the addition reaction of the hydrogen halide HBr and the HI, right, can be added to this double bond, right? As a result, you will generate this added product. Okay. But selectivity shall rise, right? You have somewhat asymmetric alkene or olefin, right, start to run or participate in this addition type reaction, right? So you have the olefin or double bond alkene here, but the carbon here and carbon there, they are not equal, right? They are different. And then you have two options, right, after electrophilic addition type reaction. Hydrogen attached to here, and in this case chloride attacked there, right, to generate the first product. Or the hydrogen added to this carbon, right, and halide attack here, the carbon next to it, which will give you the second product, right? So you have to decide, right, which is the major product, right? Or this reaction has some selectivities or not, right? So the selectivity plot on the rise if you are running the reaction with the asymmetry alkene, right? To answer this selectivity aspect of the electrophilic addition reaction, you have to recall the mechanism, right? And as I mentioned, right, the general formula or first slide of the mechanism. The formation of the carbocation, the first step, is the RDS or rate limiting step, right? So you can think about then, right, the same reaction, the proton adds to the C1 first, right? Following the mechanism we already know, right? Then the intermediate, this terbutyl cation is formed after first step, right? So this is a tertiary carbocation, right? You can think about the bottom case, proton adds it to, right, the number 2 carbon, right? The carbon next to it, number 1 carbon will get protonic charge or plus charge, right? This will gonna be the secondary carbocation, right? So first proton addition and the carbon next to it will get the protonic charge or plus charge, right? And then halide attack. The second step will give you the corresponding product respectively. Right? If you have tertiary carbocation, you will get this terbutyl chloride, right? If the reaction goes through the secondary carbocation, then you will generate this isobutyl chloride. But if you run this reaction, right, you only get this product. This is the only product you're getting. Okay? So why this is the case, right? To explain these trends, you need to understand the relative stability of the carbon cation, and this is the stability trend, relative stability of the carbon cation. And tertiary carbon cation is the most stable, followed by secondary, primary, and methyl cation. Okay, if you have more R groups around, right, with respect to the central carbon cation, more stable the species. Right? This is the electrostatic potential map. If you take a look at the bottom side, from terbutyl cation to secondary, primary, and methyl cation, and you have more bluish color as you change from left to right, right? And you have the most intensive blue, right? What indicates carbon was the highest positive charge character, right? Whereas for terbutyl cation, its bluish color is somewhat diminished and delocalized to some degree, right? Or in other words, positive character is somewhat neutralized in this case, right? So if you have more R groups, less positive on the carbocationic center, right? And this will give you the stability of the system or molecule or species, right? So RQ group is a sort of like the electron donating effect, right? Decrease the concentration of the positive charge in the carbon, right? And this can be further rationalized by the hyperconjugation effect, which we studied, right, in the previous chapter, right? This is the hyperconjugation scheme, right? You have the ethyl cation and methyl cation, right? This is a primary carbocation. Right? Which means you have the methyl group, right? Methyl group next to the carbocationic center, right? And then you can think about, right, the hyperconjugation effects can arise. You have a sigma bond orbital, the field orbital, right? Between carbon and hydrogen, there must exist a field MO, right, or orbital, right? And for the carbocationic center, right, you have the empty p orbitals, right? This carbon is sp2 hybridized, right? You have 3 arms, right? And there is one remnant p orbital, right? Sitting perpendicular to this plane, right? That is the purple orbital, which is empty. So if you have field orbitals around, right, then field-unfilled orbital can interact, right? That is the origin of the hyperconjugation, right? As we studied. By doing so, by doing this conjugation effect, hyperconjugation effect, the electron can effectively delocalize, right? And then the overall system will get stabilized, right? Electrons can occupy larger space, larger volume of the space, right? That's good. That's good for the system because you can minimize the electrostatics. Right? So that is sort of like the fundamental reason why hyperconjugation can stabilize the system. And then you can compare, right, ethyl cation versus methyl cation. For the methyl cation, there is no such like field orbitals, right? There's no CH bond or sigma bond with the field electron or orbitals, right? So there is no hyperconjugation effects around. And then you can extend this idea, right? That if you have more groups, that means more field orbitals, right? Then they are more willing to conjugate with the empty p orbitals, and then hyperconjugation effects will get maximized. Right? By doing so, you can expect, right, larger stabilization. And in this picture, you can then think about methyl group here is serving as a sort of like the electron donating groups, right? And then that will effectively neutralize the carbocationic character. That's why we're getting the diminished blue, right? Where relatively speaking, increased electron densities compared to the methyl cation. Right? 그래서 hyperconjugation effect는 우리가 conformation 다룰 때, 그죠? 공부할 때 한번 나왔었어요. stagger conformer와 eclipse conformer, stability 비교할 때 electronic origin에 대해서 설명을 할 때, 그죠? 기억날 겁니다. 그때도 field, unfilled orbital interaction으로 설명을 했었어요. hyperconjugation 이제 유기화학 공부하면 항상 많이 나오는 컨셉이니까 제대로 기억해 주시길 바랍니다. 원리는 사실 심플해요. 일렉트론이 넓은 공간에 공유가 되고 비편저화될 때 안정화가 된다. 그 안정화되는 메커니즘이 필드 오비탈에 있는 일렉트론이 언필드 오비탈로 이제 컨주게이션에 의해서 공간을 공유하게 될 수 있으면 에너지적으로 유리하다. 그 원리를 기억을 하시면 하이퍼 컨주게이션 효과를 기억하실 수가 있겠죠. 그렇죠? Right, that was the hyperconjugations and why, right? Tertiary carbon cation is the most stable in this series compared to secondary and primary carbon cation. Alright, so now you know that, yeah, this is another like energetic scheme, right? Illustrating the hyperconjugation effect. You have filled orbitals, right, or filled electrons, and empty p orbitals, and they can do some orbital interaction, which will eventually decrease the energetics of the electron in CH bonds, right, which is good for the overall system. List the following. I'm pretty sure you can do that, right? You have 3 R group here, 2 R group, and this is only 1 R group, right? So stability trends will be like that. Of course, you can think about the bottom one as well, right? The chloro, methyl, fluoro groups, right? If you think about which one is the most electronegative, in other words, pulling the electron, then you can make the series, right? Fluoro group is the most electronegative group, right? So this will pull the electron, your inductive effect, right? So this carbocation is the most, right, electron deficient carbocation, right? Followed by this one and this one, right? So then you can then make this one is the most stable carbocation, right? Third, okay? So you can choose, right, more electron-rich carbocation, right, for more stable carbocation in this stage. All right, so now you know the stability trends of the carbocation, and you are getting back to the reaction of alkene, and then you need to explain and rationalize, right, why the above pathway is the most preferable. At least now you know that this is the more stable, right? Tertiary carbocation is more stable, and the isobutyl cation, because this is, you have more R groups around, right? This one you only have 1 R group, right? This is tertiary versus primary, right? And you know that this one, the intermediate, is more stable, right? So what, right? Then why you are getting this more? You need more logic here, right? Why this one is getting faster, right? So you need to link somewhat like the energetics of the intermediate and kinetics and kinetic barrier, right? So you need to think about then the energy diagram. You learn about the energy diagram or free energy diagram in chapter 5, right? And you need some piece here to illustrate and explain, right? The kinetics and degree to which, right, the reaction is actually happening. For which you need to understand the Hammond postulate. So you are studying about the Hammond postulate for this slide and next slide, I guess, right? So you need to think about the energy barrier and transition state, right? And the basics of the Hammond postulate is all about this, right? If you have, let's say you have 2 structure or 2 different species, right? But if they have similar structures, right? Then energetically they are close. So that is the baseline for the Hammond postulate, right? So let's say if you have a reaction diagram and an x-axis indicate the progress of the reaction, right? And you have 2 states, right? And these 2 share the structure, very similar structure, and also very similar energetics, right? So this is sort of like pretty logical baseline if you think about, right, the reaction. And you can develop a little bit more, right, with this symbolized, right, reaction scheme. You have reactant state and product state, right? There's a bond between A and B, and product state, the bond is swapped, basically. So you have the bond between B and C, right? And you can imagine in between, right? In between this reactant state and product state, then you can think about sort of like transition state in the middle, right? And there are 3 different scenarios you can think of, right? In terms of like bond, right, formation and bond break, right? First scenario is this, right? If you pick the apex of the kinetic barrier, right, or in other words, the transition state, right? Your transition state may look like this. A and B is closer than the distance between B and C. In this case, you can say the transition state resemble the reactant state. Okay. Second option is the following, right? The bond between B and C is much closer than bond between A and B, right? The distance-wise. Then you can say the transition state is resemble the product state, right? And there is a case, right? Equally partitioned, right? In the middle, right? So these 3 options, right? What you can think of, right? The structure of the transition state resemble both structure, the reactants and products, right? There are some possibilities, but which does it resemble more closely? That's the question you need to think about, right? And this question can be answered by the Hammond postulate, right? The Hammond postulate states that the transition state is more similar in structure to the species to which it is more similar in energy, right? As we discussed in the previous slide, right? Very basic argument. You can apply this to the transition state argument as well. Okay? So, transition state is more similar in structure to the species to which it is more similar in energy. Right? What does that mean? Right? If you have this kind of scenario and you have transition state, structural, energetically, right? This transition state is more close to the reactant state, right? And also structure-wise, right? Transition state should be more closer, the structure is more closer to the structure of the reactant state. Okay? And this is the case for the exergonic reaction. Right? What about endergonic reaction? And your free energy diagram will look like this, generally speaking. Then transition state is closer in energy to the product state. And that's more similar in the structure with the product states too. Right? So this is sort of like the general argument for the exergonic reaction, right? With the left-hand side, transition state resembles the reactants, or the endergonic reaction, right? The transition state resembles the products. Okay. So again, the Hammond postulate is the following: the transition state resemble what it is closer to it in energy. Okay. 그래서 해먼 포스츄레이트라는 것이 결국 유기화학 이제 차들 반응의 키네틱스와 동력학을 설명하는 데 있어서 더 복잡한 요소들이 훨씬 많습니다. 근데 유기화학 정도 그리고 특히 코र्스 정도에서 다루는 유기화학 반응을 설명하는 데 있어서는 이 정도 postulate 정도, postulate라고 부르는 이유가 있어요. 가설, 가정이라는 뜻이고 일종의 가이드라인이라고 생각하시면 되는데 이 정도의 이제 논리만을 가지고도 설명이 되기 때문에 아주 범용적으로 쓰이는 겁니다. 그래서 transition state의 어떤 구조, 원 energetics가 리액턴트와 더 가깝냐, 프로덕트와 더 가깝냐, 이제 이것을 조금 단순하게 접근하는 논리라고 보시면 되겠습니다. 그래서 결국 transition state가 에너지적으로 봤을 때 어디랑 더 가깝냐, 리액턴트와 더 가까우면 structure-wise도 리액턴트와 더 가까울 거고, 그렇죠? 프로덕트와 더 energetically 가깝다. 그럼 구조도 마찬가지로 리액턴트보다는 프로덕트 쪽과 더 가깝게 생겼겠고요. 그래서 energetics와 structure를 일종의 강한 correlation이 있다라고 보는 관점, 그거를 transition state에 이제 확장을 한 것이 해먼 postulate이 되겠습니다. 그렇죠? transition state이 왜 중요한지는 이제 반응 kinetic스 관점이 왜 중요한지는 알겠죠, 그렇죠? 저희가 지난 챕터에서도 다뤘었고 결국에는 저 에너지 배리어를 이제 넘어야 되죠. 정반응에 우리가 속도를 생각한다고 했을 때 에너지 배려가 이만큼이 되는 거잖아요. 트랜지션 스테이트의 구조가 그러면 상당히 중요하겠다. 이제 키네틱의 관점에서 봤을 때 이제 받아들이실 수가 있겠죠. 키네틱스가 빨라지려면 배려가 낮아져야 되니까 트랜지션 스테이트가 안정화돼야 되겠죠. 그렇죠? 에너지가 낮아지려면 그럼 어떤 구조를 가져야 되겠는지까지 저희가 이제 생각을 확장해 볼 수가 있는 거죠. 그래서 해먼 포슐레이트이 유기화 정도, 저희가 다루는 반응 정도, 반응성을 설명하는 정도에서 유용한 논리 틀이 되기 때문에 여러분들이 정확하게 이게 무엇을 의미하는 건지 파악을 분명하게 하기를 바랍니다. 스트럭처와 에너제틱스의 상관관계로부터 시작을 해서 그 상관관계를 트랜지션 스테이트에 적용한 거다. Okay, that is about the Hammond postulate. And will the structure of the TS in the following reaction coordinate diagram be more similar to the structure of the reactants? It's a product, reactant, product. So back to the reaction. And now you know the stability of the carbocation, right? And also you know the Hammond postulate, right? And combining these two pieces, you can answer the following question, right? Why the difference is made, right? Why the other pathway is much faster. And this is the observation. The more stable carbocation is formed more rapidly. Right? You need to be able to explain this, right? Using these two piece of information we just learned. Okay? And this is the rationale, right? So you know that these red tertiary carbocation is more stable, right? We discussed hyperconjugation effects, right? And that's why this red intermediate state after first step is sitting below than blue, right? Which is the primary carbocation, right? And then for each pass, right? The above pass and below pass, you can think about the transition state will exist, right? And the transition state must be different, pass rate is different, right? So transition state must be different, right? And you know that if you know that first step is the endothermic, right? Then compared to the reactant state, the intermediate state will have the higher energy. Right? Then applying the Hammond postulate, right? Then the TS, right, transition state here and there resemble more, right, the intermediate state because they are energetically more close, right? And then now you can link the stability and the energetics of the transition state, right? The red has to be lower in energy compared to the blue if you compare the apex, the top of the mountain, right? Because the intermediate state, this tertiary carbocation is more stable than blue, right? And applying the Hammond postulate, you can guesstimate the top position for red is also sitting below than the top position of the blue, okay? Then you can explain, right, the barrier from the common reactant state to the intermediate state is small in red as compared to the blue. Right? That's why the red, the pathway for growth in this scheme, right, will give you faster kinetics. Okay. But you may notice, right, the difference in the stability of the transition state is less than the difference in the stabilities of the carbocation. And what that means is the delta here is larger than delta there. But they're just a delta still, right? The small delta that change the kinetics. Okay? 그래서 이제 carbocation의 stability 트렌드는 아까 hyperconjugation effect로 원리를 이해를 하셨고 Hammond postulate를 이해를 하셨으면 이제 transition state의 energetics와 그렇죠? 중간 체온 reactant 사이의 상관관계에 대해서 아실 수 있을 거고 근데 이제 우리가 electrophilic addition reaction에 이제 그 원리 두 개를 적용해서 kinetics를 설명을 해보자는 얘기예요. 그렇죠? First step이 electrophilic addition step의 first step이 보통 RDS라고 알려져 있고 endothermic process라고 알려져 있어요. 그걸 안다면 여러분들이 이제 free energy diagram 그 첫 번째 RDS에 해당되는 스텝에 대해서 이 free energy diagram을 그릴 수가 있을 것이고 두 개 패스웨이에 대해서 이제 차별적으로 그리실 수가 있겠죠. 인터미디엇 에너지가 빨간색 3차 카보캐라인이 더 안정하고 파란색 카보캐라인보다 안정한 거 아시고 그러면 해먼 포스트렛을 가정하면 각각의 인터미디엇이 생기는 패스웨이 1, 패스웨이 2가 있잖아요. 그렇죠? above 패스웨이가 있고 below 패스가 있잖아요. 그렇죠? 패스웨이가 다르고 인터미디엇이 다르니까 당연히 프리 에너지 패스웨이도 다르고 프리 에너지 다이어그램도 두 개가 다를 수밖에 없어요. 빨간색과 파란색에서 다르게 나타나는데 우리는 이제 상대적인 차이가 중요한 거죠. 키네틱스를 설명하기 위해서. 해먼 포스트레이트를 적용하면 이 트랜지션 스테이트, 블루든 레드든 트랜지션 스테이트가 인터미디엇 스테이트와 더 가까울 거다라고는 이제 아실 수 있겠죠. 그렇죠? 근데 우리가 이미 스테빌리티 차이를 알아요. 파란색과 빨간색 인터미디엇의 차이가 있다는 걸 알아요. 델타만큼 차이가 있죠. 그 델타가 이제 유지가 된다는 얘기입니다. 크기는 바뀌겠죠. 그렇죠? 그래서 파란색 봉우리의 결국 베리어가 델타 G 더블 대각 값이 빨간색 패스웨이 델타 G 더블 대각 값보다 이제 커지게 되겠죠. 그렇죠? 결국 파란색 패스웨이로 가는 게 느려진다는 얘기입니다. 그렇죠? 그래서 이 논리가 이렇게 이어진다라는 것을 이해를 하시면 될 것 같습니다. Right? So that's why the more stable cation is formed more rapidly. Okay? The relative rates of carbocation formation determine the rate, the relative amount of product. So again, for the same substrate, we have a choice proton addition, right? First to this C1, and carbocation is formed there, right? Tertiary carbocation is formed there, and chloride, right? That is the only product, right? Because of what we rationalized thus far. Okay. What product is formed? Now substrate is different, but I guess you can apply the same principle, right? You have a choice, right? The carbon 1 and carbon 2 are not same, they are not equal. You can consider the first electrophilic addition, is that, right? Proton addition. If you go above, right, then you will generate a secondary carbocation, right? Proton added there, right? Then you will generate proton plus charge in the number 2 carbon. That is the secondary carbocation. If you think about the bottom line, right? If proton adds first to C2 here, that means you are generating this primary carbocation, which is very unstable, right? That's why the body pathway is largely disfavored. And you can perhaps find the role then, right? The electrophile, in this case proton, right? Adds to the sp2 carbon bonded to more hydrogen, right? So as to make, right, the carbocation with more R groups, right? More substituents. Right? So you have this asymmetric olefin gain. Then proton has to add to the sp2 carbon with more hydrogen, right? Here you have one hydrogen, carbon is 0 hydrogen, right? So proton should add it there, right? And then you are generating this tertiary carbocation. And then iodide attack will give you this major carbon, right? You don't need to memorize this, right? You can just remember the principle, right? You have to think about which carbon, right? Proton addition will give you the carbocation of higher stabilities. Right? Larger substituents, more substituent in other words. Right? Same rule, right? You have this asymmetric case, right? The proton should add it there, right, to make this carbocation. Right? So you have tertiary carbocation with the proton addition to this carbon, right? And then bromide attack will give you this major product. So you don't need to memorize this statement, but this is a general argument. 그래서 뭐 말코니프를 해가지고 뭐 이렇게 스테이트먼트를 만들어 놓은 것들이 좀 있어요. 이 스테이트먼트도 제너럴한 표현은 맞긴 맞는데 이거를 외우시지 말고 왜 이거인지 원리를 아시면 뭐 이걸 외울 필요가 없잖아요. 그죠? 프로톤이 왜 더 많은 하이드로젠을 가지고 있는 카본 쪽에 붙어야 돼요. 붙고 나면 우리 옆에 쪽이 카보캐라인이 되니까 수소가 더 적은 쪽에 프로톤이 플러스 차지가 생겨야 더 카보캐라인이 안정하잖아요. 그러니까 프로톤은 당연히 타임젠이 많은 쪽, 다른 말로는 substituent가 적은 쪽으로 붙어야 그 옆에 쪽이 플러스 차지가 생기니까. 그죠? 뭐 외우는 걸 말리진 않겠으나 원리를 기억하시라는 이야기입니다. Electrical addition의 첫 스텝은 electrifying 올레핀에 붙고 카보캐라인이 생기는 스텝이니까 더 안정한 카보캐라인이 붙는 쪽으로 생각을 해보시면 되겠죠. 더블 본드에는 카본이 2개가 속해 있으니까 둘 중에 하나 선택을 하시면 되겠죠. Right, and this is the terminology when you encounter selective ratio, right? And ratio selected, that's the first terminology you learn. Your selective reaction is a reaction that forms more of one, right? One constitutes more than another, right? And then you can put the adverb, right? Moderately reduce selected, highly reduce selected, completely reduce selected, right? If you have your one product, like this case, then you can say completely reduced selected, right? Okay. But what about the bottom case? You are generating major versus minor, right? Perhaps in this case you can say highly reduced selected, but this is somewhat subjective expression. So, but what you should remember is the reduced selected. What is reduced selective means? That means the reaction give you one constitutes more than another. Right? And then you can think about stereo selective reaction, right? As well. If your reaction is generating more than one stereoisomer, and if the reaction give you one more exclusively than other, then you can say stereo selective reaction. Right? There's more terminology like chemo-selective, but I guess you don't need to know for this course. What about this case? You have almost symmetrical olefin, right? RT. You have methyl and ethyl, right? And then first proton addition will give you both, right? The secondary carbon cation. The methyl versus ethyl, the effect is quite minute, right? That's why you're getting almost 1-to-1 ratio of that. In this case, you can say the given reaction is not reduced selective. With a major product obtained from the addition of HBr, right? This is the reagent for the following. Right? Then, if you remember, first step is the electrophilic addition of the proton, right? And generating carbocation. Then you can answer, right, easily. So this should be the spot, right, to generate the secondary carbocation. The proton should add it here to generate this tertiary carbocation. Then bromide attack, of course, will give you the corresponding added product. Right? Proton should add it there to generate this carbocation, tertiary carbocation, and bromide attack, right, to give you the corresponding product. Here, first step, should add it there, and halide attack there, right? Here, halide, sorry, proton addition, and halide attack there. This is the symmetrical case, but this will give you one. Okay. So in this case, right, you get only one product. Right? So still, the reaction give you the same product, right? Because it's completely symmetrical case, right? So either this or either that, right, will give you the same product. So you can still write down the major product in this case, right? And I guess you can try to solve this one and this one, and then we can check the answer. And I guess this is everything we're going to discuss for today. And then we can continue on next week, I guess. So, 오늘은 수업을 여기서 조금 일찍 마치도록 하고요. 다음 시간에 이어서 알켄 리액티비티 조금 더 다루고, 저희가 이제 알켄의 리액션 다 다루고 나면 이제 알카인으로 넘어갑니다. 알카인은 알켄과 많이 닮아 있어요. 유사한 이제 메커니즘과 유사한 논리가 적용이 됩니다. 네, 그럼 오늘 수업 여기까지만 하고 다음 주에 봅시다. 네.